Hello and welcome back to AP Pre-Calculus. Today's lesson is 3.4 and 3.5, sine and cosine function graphs and sinusoidal functions. I'm just going to read this page. So far in Unit 3, we have learned how to define sine and cosine values for angles in standard position, how to measure angles in radians, and how to use the unit circle to evaluate sine and cosine functions at given angles. Now we will put all of these ideas together and discover how they can help us develop and understand how to represent sine and cosine functions graphically. So now we're going to graph the sine and cosine function. Let's start by considering the function f of theta equals sine of theta. Since we know that angle measures in standard position are periodic, we can expect f of theta to be periodic. Also, since theta is our input value, we will use the horizontal axis for our angle measures and the vertical axis for our output values, f of theta. So our x values will be angle measures, pi, pi over 2, pi over 3, 2 pi over, all those kind of things. And then our y value will be the heights of those functions if you were thinking about going around the unit circle. All right, so here we have the unit circle over here on the left. We have some tables that we're going to do some input output things, and then we're going to graph those. So we are graphing sine of theta. Okay, so we're going to start at 0, right? What is sine? Well, first of all, what value is the sine value in the ordered pair? Well, sine goes with y. So starting at 0 pi, what is our y value? And that would be 0. Okay, and now let's fill in the rest of these numbers that we have up here. What is sine of pi over 6? 1/2. What is the sine of pi over 3? Square root of 3 over 2. Pi over 2 is 1. 2 pi over 3 is square root of 3 over 2. 1/2. And then back to 0. Okay, so let's go ahead and graph that. So pi over 6 is 1/2. I'm going to skip pi over 3 for a second because I don't really know, but I know it goes up there. I'm going to skip the pi over 3's for now. I'll come back to them. Pi over 6 was easy to graph. And then pi is back here. So I already know my graph does this kind of thing for that first part, right? And then let's do the second part. It's going to be the same numbers, basically, but they're going to be the negatives because we're on the bottom half of the graph now. So negative pi over a negative 1/2, negative square root of 3 over 2, negative 1, negative square root of 3 over 2, negative 1/2, and back to 0. So to graph those, I know that I'm here at 7 pi over 6. Again, I'm going to skip the pi over 3's because they're a little bit harder to graph, but you can kind of estimate if you want to use your calculator and figure out what it is. And then we could just finish up our graph like that. So there is a very shaky sine curve. That's one period of the sine curve. And it should make sense that it took 2 pi to complete the whole thing because we had to go around the whole circle. But I could keep going around the circle and I would just keep repeating this same little sideways S curve over and over again, going up to 1, going down to negative 1, because that's as high as I could go on a unit circle in the graph. It's as low as I can go on the unit circle. I could actually go backwards and my graph would go in this direction, keep making that little sideways S curve forever and ever, because I could go around the circle as many times as I want to. All right, this page has some vocab that we are definitely going to have to know. So we are dealing with the sine curve. All right, so the first thing is the midline. You may have heard of it before, but the midline is the line that basically cuts your graph in half, okay? It goes through the middle of the minimum and maximum values. For our function here, f of theta equals sine theta, that's as basic of a sine curve as you can make. We've done no transformations to it, so the midline would be y equals 0. Midline will always be a y equals thing because it's a line, okay? All right, what about the amplitude? Well, the amplitude is how high and how low it goes from that midline, all right? Amplitude is always positive, okay? If I ask you for amplitude, even though it might be a -3 out in front of the sign, we would still say it as a positive. But for the basic f of theta equals sine of theta, the amplitude is 1, okay? Period. How long does it take to complete this S-curve? Well, it took 2 pi in the basic f of theta equals sine of theta. Later on, we're going to do transformations, so that's going to change up a little bit, okay? And then last, the frequency. The frequency is the reciprocal of the period, all right? So the frequency in this case would be 1 over 2 pi. So the graph of f of theta equals sine of theta oscillates between concave up and concave down. Hopefully that's not new vocab to you, right? So if we're talking about here, we're starting to be concave down, and then we turn to concave up. What would this be called? This would be called a relative maximum. This would be a relative minimum. What about the point where we turn from concave down to concave up? Like right here, that's called a point of inflection. All right, let's do the same thing with our cosine graph. We're going to write down the numbers. We're going to get a starting point because I don't have 0 in our table. So let's start with 0. Remember, cosine is the x value of all my ordered pairs. So if I'm starting right here at 0, what is my x value? And it's 1. So I'm going to come down here at 0 and go up to 1. So I'm going to start there. So I'm already starting at a different place than my sine curve. So pi over 6, square root of 3 over 2. Let's try and guesstimate this time. All right, somewhere in there. Then 1/2. So now we're here. Then pi over 2 is down to 0. So we're here. And 2 pi over 3 is negative 1/2 because we're on the left side of the graph. Negative square root of 3 over 2. So now we're down here, then we're here, then we're here, and then back to pi. Oh, I already wrote it down, is 1. So far we've gone from here and around the circle, and we're here. So now we're going to go the other half of the circle. We're still on the left side of the y-axis, so my x is going to stay negative, so square root of 3 over 2, negative 1/2, 0. Now we're back on the right-hand side, so 1/2, square root of 3 over 2, and then we end up back at 1, okay? So let's see where we at here. So we're point there, point there, point there, point there, point there, and point there. So let's see if I can make it so not so shaky this time. All right, so we're coming down. There we go. And that's our cosine curve. And just like the sine curve, this goes on and on forever. And if you can kind of picture it in your mind, when it redoes this same little period graph here, it's going to kind of look like the s function for the sine function just moved over. And that's exactly what it is. It's the, remember I told you that you could, in a periodic function, you could grab it and slide it to the left or the right, and you could get it right back on top of each other. I could slide the cosine graph and get it to fit right on top of a sine graph. I would have to shift it about pi over 2 to the right, and then it would be the exact same graph as the sine graph. One more little thing about our sine and cosine graph before we move on is I want you to start thinking of the way sine and cosine start from the y-axis, from the 0 angle measure, okay? Sine starts at 0 and goes up. It will always start at 0 and go up if it's your normal sine curve. If it starts at 0 and goes down, then something has to have changed that. And cosine starts at 1 and goes down. So from here on out, I want you to think about that, because if we see it starting there and doing something different, then something must be affecting our normal cosine and sine graph. The properties of the cosine graph are basically the same properties of the sine graph. I mean, if you think about what I just said, that I could slide the cosine graph over far enough and it would become the sine graph, it makes sense that they have the same properties. So here we have a word that's new to a lot of us. sinusoidal functions. That's just your sine and cosine function, but they have transformations, okay? If we're dealing with just the sine function or just the cosine function, we don't really worry about it. But if it has any kind of plus signs or minus signs or numbers being multiplied, then we consider them sinusoidal functions. For example, this guy. He doesn't meet the normal f of theta equals sine theta or f of theta equals cosine theta. It starts at 3 and goes up, and it doesn't go down in the negative. So there's definitely some things going on here. So let's figure out what these four things are. Let's figure out the period first. So I'm going to copy starting at 3. I'm going to go along the line here. And when do I get back up to 3? Right there, right? So my period is pi. Next is frequency. And on our notes, we should have saw that frequency was 1 over the period. So it's 1 over pi. The midline. All right, the midline is the thing that cuts this in half. So there's the midline. So our midline is y equals 3. Remember, a midline it's a line. We have to have y equals there, okay? And amplitude measures from that midline how high and how low did I go. I went 3. Now look what we did. We started, if I start at the y-axis where my angle measure is 0, I started at the midline and went up. That's a sine curve, right? Now I could, later on we'll find out that I could rewrite any sine curve as a cosine curve. I just have to shift things around a little bit. Let's try it again. All right, so I'm starting at 3. I'm going down, so I want to get back up to 3. I got back up to 3 right there. How long did that take me to get there? It took pi over 2. Our frequency is 1 over pi over 2. Well, we can't leave it like that, so we have to fix that up a little bit. So it is 2 over pi because we keep change flip. All right, let's look at that midline. Where can I cut this in half? Well, I think if I go right here, I have the same, that's supposed to be on that y equals 1 line. So y equals 1, and then how far up from there did I go and how far down did I go? We went 2. Okay? Let's run back to that midline real quick. If you're ever not exactly sure what that midline is, you can find the average of your highest point and your lowest point. So my highest point is 3, my lowest point is -1. Average means add them together and divide by 2, and you'd get 2 over 2, so it's y equals 1, okay? And if you want to get the amplitude, you could do the same thing, but you'd have to subtract them. I could do 3 minus -1 and then cut that in half. Example 3 here is a word problem, right? They don't give us a graph, they don't give us a chart, and remember that's one of the 3 things that we're going to have to be able to do is to look at a graph and solve, look at a chart and solve, look at a word problem and solve. So let's read this. A sinusoidal function h of theta has a maximum, so that's a keyword, maximum at the point pi comma 8. The first minimum after reaching this maximum value occurs at 3 pi -2. Find the period, the frequency, the amplitude, and the midline for the graph. Okay, so when we go from a high point to the next low point, that only gives us half of a graph, right? So how far did we go to get half of a graph? Well, high point was at pi, low point was at 3 pi, so we went 2 pi to get half of a graph. So how far would we have to go to get the whole graph? That would be 4 pi. Frequency is easy. Once you know the period, you do 1 over 4 pi. Midline. So this is the part where you might want to do what I told you in the last slide there. Add them together, cut them in half. Find the average. So I got 8 plus -2 over 2. And what is that going to give me? Y equals 3. And from there, you can go, okay, well, how far do I have to go from 3 to get up to 8 or from 3 to get down to -2? And you could say 5, but you could do this, 8 minus -2 over 2. That becomes 8 plus 2 divided by 2 is 5. All right, this question might look a little familiar, but let's go ahead and read it. The figure shows a large clock mounted on a vertical wall. The clock has an 8-inch long moving minute hand, and the center is 120 inches directly above the floor. So if this point right here is 120 inches above the floor, and this is 8 inches long, what is the highest point that the arrows, like the pointy part of the arrow, would be? And we could put, well, that's 128. Well, what if it was pointing straight down, like at the 6? Well, we'd go up to 120 and go down 8, and we'd be at 112. And we know the midline is 120. Okay, we didn't get to the midline yet, but we know that the center of the clock is 120. All right, so at t equals 0 minutes, the minute hand is pointed directly at the 12. However, the clock is not working properly, and the minute hand is going twice as fast as it should. Thus, the next time the minute hand points directly at 12 is 30 minutes. Well, what does that tell us right there? That tells us that the period is 30 minutes, right? All right, as the minute hand moves, the distance between the end of the minute hand and the floor periodically decreases and increases. The periodic function h models the distance in inches between the endpoint of the minute hand from the floor and the floor as a function of time in t minutes. So question A here is asking us to find the points for F, G, J, K, and P. I think we've done this before, but let's do it again. So we're going to start at 0 minutes, and we are 128 minutes above. All right. I'm going to go and finish the period. This might be easier. How long did it take us to go around that clock? Remember, it's going too fast. So 30 minutes, I'm back up to 128. So when would I be at the bottom? Well, I believe that would be at 15 minutes, right? Which would put us at 112. When am I exactly 120? We could go cut those in half. You got 7.5 is 120. And then I believe it's 22.5 is 120. So there are my 5 points. All right, let's move on to the next question. Okay, so B says, find the period, frequency, amplitude, and midline. So we already know that the period is 30 minutes, right? Frequency, 1/30. Amplitude, well, I went from 120 to 128, so it's 8 inches. And then what's last here, the midline, y equals, and this is our midline right here, and the y value is 120, okay? So find 2 intervals for which the graph of h is both decreasing and concave up. So I want to be going down for my y value, but I want to be an increasing slope, okay? So this is increasing, so that's no good. So I'm gonna do the blue in bad one. So all increasing, I'm doing in blue. All right, so it can't be any of those because in those periods it is increasing. So the other F to G, G to J, and P on is, well, we don't have anything else. So our only 2 choices are F to G or G to J, or the whole thing F to J, I guess. So from F to G, I'm decreasing, so that part's good, but that is still concave down, and I want to be concave up. So I want this part right here. That's the only part that's good. Now, it'd be nice if we could just write our interval, but we want to be a little bit more communicative in our answers sometimes. So this is what we're going to write. We're going to write H is decreasing and concave up. See, I'm just using the wording of the question to give a better answer with some context, right? In the interval, and I don't have to put the interval, we just label the interval from 7.5 to 15, right? And we don't include those because that's our points of inflection and our min, but so we use our parentheses. If this weren't an AP class, like if this was just regular pre-calculus, we probably could get away with saying, well, it's, from G to J. But we have to be a little bit better in our answers if we want to get college credit.